Hello, in this video, I am going to challenge your common sense. There are different types of lengths. Let's think about what's the length of the curve and how to sharpen your intuition. I found that sometimes the length of the curve I imagine differs from its actual length. I'm curious about that. There are several videos about this on the internet, such as one where pi seems to be not about 3.1415 but 4. Many of those videos end with "that's mysterious" with no explanation why. That bothers me. I don't want to stop there. The fun part is understanding why it happens, and sharing that fun is why I am making this video. I have a vague sense of what length is, but I find it difficult to put into words. Please try to define the distance without using the word distance or length. It's hard to describe. In this video series, my goal is to think about the length of a curve. In this first video, I focus on how length can mislead your eyes. For example, I show a situation in which straight path and a detour path look to have the same length. Another theme in this video is intuition and learning. I value intuition. Intuition is important for me. But I need to check my intuition with logic. Because my intuition often goes wrong, I need to double check. Especially when I first encounter a new idea, my intuition often fails. Probably because my understanding is too shallow. While learning, there are moments of something is wrong. At those moments, I see the limits of my intuition and my understanding. I like such moment. It's fun. We can update our intuition by learning. My intuition is very close to a feeling. So even when I was wrong, it's very hard to see my own mistake because it feels right. That is why I always need to check my intuition. Deepening my understanding sharpens my intuition. Intuition and feelings are both valuable to me, but there is no guarantee they align with reality. I want to understand the universe a little bit. I feel the universe has personalities. Like gravity, we know a lot about how gravity works, but we don't know why the universe has gravity. I feel gravity is one of the personality of the universe. For me, learning means aligning my perception of the world with reality. I could believe what I feel should be real, ignoring the world as it is. I could also believe who you should be, even if it means ignoring who you really are. But I want to understand the universe as it is. I want to know who you really are. That's more fun to me. Therefore, I constantly want to refine my intuition. It's a joy to feel my intuition expand and my world expand. I actually don't know how to share this feeling with you, but my wish to share this joy is another reason to make this video. Now to the more concrete part. This video talks about length and distance. In fact, there are many distances, not one. In this series, I focus on Euclidean distance, Manhattan distance, and Hausdorff distance. In this video, I would like to talk about Euclidean distance and Manhattan distance. Let's begin with the Euclidean distance. If someone says distance, it's usually the Euclidean distance. It is a distance on a flat plane, where the shortest path between 2 points is a straight line. Back in my high school, I thought this was the only distance. But on a curved surface like Earth, movement has to follow the surface, so the shortest path is not the straight line. As examples, there are also special distances, like the shortest path by train or along the actual road, which are not straight. You need to follow a path. For Euclidean distance, the triangle inequality holds. There is a triangle, the length of any one side of a triangle is less than the sum of other two sides. Simply put, between 2 points, going straight is always shorter than the detour. Euclidean space holds the Pythagorean theorem. In my high school time again, I felt the Pythagorean theorem was a universal truth. But later I learned the Pythagorean theorem is just a special case. I was shocked. However, in everyday life, it holds almost always. A detour is longer than a straight path. It sounds obvious, but let's doubt the intuition. I made an animation to support the feeling. Consider going from point A to point C. Let's compare going straight along AC with taking a detour ABC. This animation shows that the straight line AC is shorter than the detour ABC. This is not a strict proof, but it supports the intuition that the straight line is shorter. And this is triangle inequality. Apart from Euclidean distance, there is another distance called Manhattan distance. Manhattan distance is also called taxi cab distance or city block distance. Manhattan distance is a distance when moving a city with a grid of streets like Manhattan, Tokyo, and so on. Let's see the Manhattan distance looks like. Imagine a town with a square grid of roads. Suppose we are moving point A to point C. There are many paths. One is going around, taking a zigzag that looks diagonal, and so on. Which path is the shortest? Or are they all the same? People who actually live in such cities may have a good intuition about this. Because of the triangle inequality, some may feel that the yellow, more diagonal-looking path should be shorter. Let's check about it. If I move horizontal part of the zigzag path to up and vertical part to the right, did you notice that I didn't stretch or shrink the path segments? I just cut and moving them. That means the total length doesn't change. Just up, just right. So these two paths are the same length. The animation is a visualization, not a strict proof, but these two paths have the same distance. Any other paths also have the same distance unless they don't go backward. Again, I do the horizontal part to up and vertical part to right. So these paths are the same length. How is your intuition? Did you feel each path has a different distance, or did you feel the zigzag path has a shorter? If so, you might feel confusion now, but that is a good sign. Please watch the animation again and think about it. Now you could expand your inner world. You can update your intuition. I am interested in thinking about distance in such a city. Next, let's make the grid finer. First, let's look only the horizontal segments. I cut the horizontal segment half and move. And each of half and move again and again. Then I do the same to the vertical lines. Cut and half and move. Cut half and move. I repeat this process again and again. During this process, no segment is stretched or shortened, so the total length never changes. But the zigzag path looks closer and closer to a straight diagonal line. But now there is something wrong. I show two different paths. First I said a detour path is longer than the straight path. Then I said the both paths have the same distance. So one path is longer and at the same time both paths are the same length. This is a contradiction. Have you ever thought deeply about distance? I had never thought much about the definition of the length until I met this problem, so I was confused. I thought both are right. It looks right or it feels right can mislead me if I am not familiar with the problem. I was untrained. I felt something was wrong. At that point, I realized I still didn't understand something. What kind of intuition could I gain by learning? This video series aims to train your intuition a little. In Euclidean distance, the diagonal line is indeed shorter. Using the Pythagorean theorem, the detour path has a length 2, while the straight diagonal path has length of the square root of 2, approximately 1.4142136 and so on, which is less than 2. You can draw this figure on paper and measure it with a ruler and then confirm it. Do you notice that I just define a length as something measured with a ruler here? You can doubt that definition. However, for line length, this is not bad. Here, I assume this is correct. I mean, going straight is shorter than the taking detour. In terms of the triangle inequality, for a triangle, the length of an edge is less than the sum of other two edges. So, if the Pythagorean theorem is correct, is the Manhattan distance wrong? Let's prove the Manhattan distance is independent of a path. First, let's consider the horizontal component, the x direction. Let each horizontal segment on the zigzag path have a length x di, and let the corresponding segment on AB has length of d-xi. Because everything is drawn on a square grid, every segment pair dxi and d-xi form a rectangle, since the opposite side of a rectangle have the same length. So therefore, dxk is equal to d-xk. Each corresponding segment is the same length, thus the sum of them is also the same length. Therefore, the total length of horizontal segments of the zigzag path is the same as the length of line AB. The same idea applies to the vertical component, the y direction. Each of the lengths is the same, therefore sum of the each lengths are the same, that's equal to BC. Therefore, under Manhattan distance, all such paths from A to C have the same length. But the two conclusions still contradict each other. Both seems correct. Something is wrong. I have a few hints. First hint, think about what it means to looks like a diagonal line. Looks is about the sensor, the eye. Human vision is amazing to me, but it has limits, and things are not always as they appear. You see an illusion everywhere. Feeling is matter of perception. It may differ from reality. And the second hint, what lengths do I measure? Are those two distances, Euclidean and Manhattan, measuring the same thing? In the first place, what is distance? Do you have any idea how to calculate that looks like a diagonal line? I have already shown a hint in this video. I think it is fun to think about that yourself. In the following video, I will do the same things on a curve instead of a straight line. I use the popular internet example of pi is 4. In the end, it says the same thing as the straight line case discussed here. It leads to the question, what is the length of a curve? And that is also, what is the definition of the distance? Then I want to discuss why this contradiction happens. Let's train your intuition. Thank you for watching.